Let's cover another application of principal virtual work. We'll be covering the torsional problems of elasticity, and torsional problems becomes very important. For example, if you have an airfoil, that airfoil, the behavior of the airfoil is going to depend not just the bending stiffness, but also the torsional stiffness. And the geometry of the cross section, which is quite complex, can become an important role in really determining how, uh, for example, the airfoil problem, how that cross section is going to behave. And so torsion problem is actually very important in this field of aerospace applications. And so for that reason, I'll be covering that today. Um, and so we're going to consider the torsion. I apologize. I don't like the red pen because the red pen reminds me of somebody grading me very harshly. So we'll use a black pen. Torsion of a uniform bar. And we'll be then deriving and looking at that problem. So say you have a cross section that looks like that for a bar, and I'm not going to pretend I'm going to draw this cross section perfectly next time. So I apologize if it looks disconnected there, but it is a connected domain, um, and this is S, so it's enclosed by S. This curve C, for example, and the coordinate is S, and then the area here is A. And I'm going to now consider the length of the bar as L along the x-axis. The cross-sectional area is A. And we have C is the edge curve of area A. And then we have S as the arc length, C. And then I'm going to apply a prescribed torque. Prescribe a torque at Z equals L. And I'm going to consider, and again, I told you I was not going to draw a perfect cylinder, and I didn't do it again, so I apologize for that. I patched it though. You should be very happy. We have the moment applied on this end, at this end here, um, and then we have the coordinate system, which I want to really cover, so it's clear what they look like. You have a, it's I'm trying to draw. I don't know. I was trying to draw that. Uh, Okay, just pretend that this is the same cross section as the one here. I apologize if it doesn't look like it. Um, and then you have this is z axis, and that's your x axis, and this is your y axis. And this deflection here I'm gonna call u. This deflection I'm gonna call v. And this is w. That deflection is w. So hopefully it's clear what the problem statement is. We're trying to understand the torsional behavior when you apply a moment. Um, that's a better line. And I'm going to continue looking at. We're going to start looking at the boundary conditions a little bit more now. So so let's look at that right now. So surface area at, and that's not a good way of writing area. And I'm sorry if I'm writing cursive. I can also write non-cursive. I just like it. It looks nice. We have this as a deflection approximations. Um, so we have this. We're going to say the traction. So let's look at what this really means. The traction, okay, at z equals 0 is 0. So what I'm saying there is that the traction on this surface right there behind is 0, and the traction on this surface is 0. So there's no tension load applied, is what that's saying. That's really what that's saying. That at this cross section here, I'm not applying a tensile load that causes cylinder to expand. I'm also gonna say there's no tractions applied on the surface here. So if I look at a surface element here, that surface element, I'm gonna say that there's a traction there. Say, um, we're gonna say that on the lateral surface, I'm gonna assume that uh, we have a traction-free surface. So no traction is applied on the lateral sides. We're only applying a moment here, and at z equals 0, which corresponds to this point here, at z equals 0, um, at z equals 0, we're applying a moment. At z equals 0, you can see here that we're applying, we're saying that the deflection is 0 and v is 0. Um, yeah, so in other words, the deflections are 0 at that point. It's fixed at that point. So traction surface is also traction free surface here on this lateral surface there. So hopefully the conditions of the problem are very clear to you, and um, we can then start trying to figure out what is going on here. Uh, and I first want to talk a little bit about what is going on this surface. I want to look at this surface more carefully because I said I'm applying a moment M, but it's not clear how you do that. It's not clear how you do that. Um, I'm particularly not sure how to do it. Well, I should know because I'm the one teaching. But why we don't start learning about um, some of the key points of this theory? So let's start talking about it. So torsional theory uh, is called Saint-Venant's displacements. And in this theory, what we're assuming here, we're assuming that this point P is going to move rigidly. It's going to rotate rigidly. So say this at an angle theta. We're going to say that this rotates rigidly to this point P prime. At a location alpha z. So it's going to move some amount alpha z at a particular distance z. But it's going to move rigidly to that point. So it's going to move to that point. So clearly, when I look at the coordinates, I want to look at the coordinates of this point. The coordinates of point P, what are the coordinates of that? The coordinates of point P is clearly, if this is R to that point P from the origin, O, then point P, the coordinates of that is R cosine theta, R sine theta. And this theory, again, it's a theory, it's an approximation, so there should be some errors in the approximation. Point P prime now is a little bit different. It's R cosine alpha z plus theta. Okay? And then you have R sine alpha z plus theta. So therefore, the deflection, how much deflection I had, it really depends on how point P moved to P prime. And so that's simply a calculation that we can do very easily. That's whatever coordinates I have at point P prime minus the coordinates at XP. And I know what that is. That's R cosine alpha z plus theta minus R cosine theta. And I can expand that. I can expand that a little bit. So let's expand that. And you can see here that I can employ small angle approximation. Okay. I note that sine theta is approximately close to theta. You've heard of that before. That's one thing that you've heard in the past. But theta can be large, so I want to be careful. Sine alpha z is approximately equal to alpha z for small rotations. So if this rotation is small, then sine alpha z is close to alpha z. Here, you also have that this is approximately equal to, for small angular approximation, that's close to 1. So the r cosine theta cancel with this r cosine theta, and you're left with the fact that you have the minus r sine theta times alpha z. But this right here is really y. So you have minus alpha yz. And similarly, I invite you to do this at home, but you can also show that v equals is going to be equal to alpha xz. I invite you to do that at home and check it out. And then I also want to make sure you understand that this v, this u is a function of x, y, and z. This v is a function of x, y, and z. But now I made it dependent only on x and z. And then this one only depends on y and z. And then I have the out of plane deflection w, which I'm not going to prescribe. I'm going to say that w is x, y, z. It depends on a warping function or some sort of unknown function. I don't know what the function is, but represents the warping that I may have of the cross section out of plane. So when you torque something, when you apply torsion to something, the cross section will go out of plane, and this is taking care of that. So let's look at this physically together. U and V are really talking about here the deflections in plane to the cross section. W is out of plane and talks about when I apply a torque, that cross section can come out of plane. And so that's what this function is doing for you, is really enforcing that. So hopefully that makes total sense. So now I can go in and I also want to comment that uh, in this theory, I'm applying a, a a load m, right? But here alpha is unknown as well. I don't know alpha, and I'm assuming that the deflection, um, the torsion, is going to occur as a function of alpha. For example, at z equals 0, you can see that u and v have to be 0 because I told you that at z equals 0, u and v are fixed. You can see here that it works out that u is 0 at z equals 0 and v is 0 at z equals 0. It's working out. So u and v are fixed. And what I'm saying is at a location away from z, so at z, we're having a particular amount of rotation, which I'm calling alpha z. At z equals L, that rotation has become alpha times L. So hopefully that is very clear to you what is going on. U and V, in-plane deflections in the cross-section. W is the result of the cross-section coming out of plane due to um, the said motion from the torque. So now I'm going to apply the internal virtual work. So let's calculate. So again, I'm deriving a new structural theory. I've derived axial bar theory or the Bernoulli beam theory. I've developed Timoshenko theory, and today I'm covering Saint-Venant's torsional theory. So calculate, which is extremely important in aerospace applications. Calculate the internal virtual work. And the internal virtual work can be found as the internal virtual work equals the integral from 0 to L. And then I have the integral of the cross-sectional area A, and I have sigma xx del epsilon xx. I can use sigma ij, epsilon ij, why not? But I decided to just use this convention. Why not either? You can't stop me. We can all have fun looking at what's going on here. I apologize. You moved away. That's my internal virtual work right there. I have a dA that I forgot. And so that's internal virtual work. And now I have to figure out what is zero, what is non-zero. So you can clearly see from the approximations that we have. Let me write them out for you so you can see them clearly. And then you guys can really work it out and see if you're getting the same thing I am. I think it's worth doing it. And then you have the warping function. And alpha here is a constant, right? Alpha is a constant. We don't know what it is, but here it is. So here is what we have. Um, so epsilon xx is the derivative of u respect to x. And here clearly I don't have, that's zero in our problem. Epsilon yy is the derivative of u respect to z, y, and that's zero in our problem. That v, respect to v, I apologize. And then have epsilon zz, which is clearly not depending on z, so the derivative of w respect to z is also zero. So actually things are simplifying really quickly for us. If we can do epsilon twice this one, so it's the derivative of u respect to y plus the derivative of v respect to x. And that, interestingly, is minus alpha z plus alpha z. So that's also zero, interestingly. Twice epsilon xz. Now that's getting more interesting now. That's that derivative is minus y alpha plus k comma x. Right? So we can do that calculation very quickly. Yeah. So that's very easy. Twice epsilon yz equals x alpha plus kappa comma y. You can do this very quickly on your own right now. Partial u respect to z plus partial of w respect to x. And that's a partial of u respect to partial of v respect to z plus partial of w respect to y. So you should be able to get exactly what I got. So the only non-zero strains are these ones. Remember, that's step number 2. Calculate non-zero strains, which we did. Now we can calculate the virtual, apply the virtual function or the virtual quantity to that. And when I do that, I'll get that internal virtual work. So substitute this non-zero strains into the principal virtual work, and then we find the internal virtual work equals the partial from 0 to L integral over the area, and then I have the only non-zero term is tau. I apologize again. Not tau, I'm using sigma. I'm applying the virtual strain now. Very nice. This is coming out very nicely. And unfortunately, if there's an error, we'll have a problem because I'm not following anything right now. I'm just going by my memory of how this works. You don't need a book when you're deriving structural theories if you understand the ideas really well. So hopefully we're not making a mistake here as I move along, because that would be dangerous for all of us here. So that's internal virtual work. And everything looks pretty clean. There, you can see that del alpha could factor out. And it's not really a function of anything, it's a constant. So it is worth kind of writing differently, 0 to L. And then you have over the area. And I'll just mix some terms together here. X sigma y z minus y sigma z x. So I've combined this term here and that term right there. There's no reason why to keep them separate if I can bring them together. dA dz. And then all this del alpha. I can bring the del alpha out since it's a constant, doesn't depend on anything there. And then I have plus integral 0 to L, integral over the area. And then I have sigma yz kappa del kappa comma y plus sigma xz del kappa x. And now that's dA and dz. So now I want to look at that external virtual work carefully. I think it's worth looking at the external virtual work. Um, the external virtual work is more tricky, and we have to be careful on how to handle that. So, external virtual work. The external virtual work can be found, if you remember, is equal. There's no body forces, so bi del ui dv. That's zero. There's no body forces, but you still have this one here, ti del ui dA. And I'm going to focus on, and I'll just expand it here for you so that you know what this looks like in non-index notation. I think sometimes it's useful to see it that way so that we're not confused. And this is a horrible situation because there's a del there, so I should get a 0 if that was an exam, but I won't because I'm the one teaching and I'm not grading myself. But again, I'm also being um, doing this real time, and so for the for the exam, you have to go and really work it out carefully. Look for any errors because conceptual errors will cost a lot of money, and money's points here. Okay, let me so let me remind you what is unknown here. When I look at the deflection U V, the only unknown here is alpha, and kappa. So somehow when I apply a torque, I need to find how much it torqued by. That's what the alpha is telling us. And then it's going to tell us what the warping function kappa is. So the unknowns are really alpha and kappa. So I should have two equations at the end, hopefully. Two equations, hopefully. Um, and I went there for a reason. I want to substitute this deflection here. And also remember, we're not applying any tractions on this surface. This lateral surface, no tractions, only on this surface here. So therefore, I'm going to focus on that surface when I do this traction calculation. This traction calculation is 0 on the lateral surface, only exists on the z equals L surface. Very important consideration. Let's look at what that looks like. Double integral a tx, and this is only at z equals L. Remember, I'm only applying it on that location. In fact, I don't want to write it there, but just remember that this A, we're really looking at z equals L there. That's what that really is. And then del U, we already know from what we did, there's minus yz del alpha. And then we also have plus ty, and then we also have xz del alpha. And so then I can continue now. Um, and this is at z equals L. I think it's important to put z equals L because I want you to remember that I'm only applying a traction at z equals L. If you recall, this right here corresponds to z equals L. So that's why I need to make sure I'm tracking that as z equals L. So this is times dA. And yeah, so I'm getting closer to reality here. Um, Let me see if I remember correctly, but this del alpha here is not a function of dA. And when I'm plugging z equals L here, everything comes out of the integral very nicely, actually. So I'm going to, if you don't mind, I'm going to write it here, double integral over the area. And I'm going to go straight for it, minus y tx plus x ty, and then I'm going to make the step of taking everything outside and saying that this is del alpha, and there should be an extra L here, right? Because that z evaluated at x z equals L, clearly that's a constant, so that comes out of that integral, I get this. So the external virtual work, very, very cool what we got. Now the question is, what is the meaning of this? It's not clear what the meaning of that could be. Um, but I'll show you what the meaning of that is. Let me draw that for you. Why we don't draw the cross section at z equals L. So again, this is my cylindrical bar, and this is z equals 0. At z equals L is where I'm applying the moment, right? That's where I'm applying the moment at z equals L. And that's what I'm showing here. I'm showing that cross section there, this one here. So let me erase these lines because they're on my way. I was just trying to get fancy here, but sometimes going fancy is not the right answer. X, Y, and let's select element here, and let's examine what this means. So when I look at this, it says Tx, okay, a load Tx. So what does that mean, a load Tx? There appears to be a load going that way on that surface. And then when I look at Ty, there appears to be a load going upwards. And this distance here, is y. And this distance here is x. So in reality, this is very interesting. This is a dA, an element area dA. So when I look at that carefully, I am really calculating a moment because Ty times x is this right here. And then I have minus y tx. That's a differential moment right there. Um, that's a differential moment right there. So clearly I'm calculating a moment without realizing I'm actually calculating a moment. And so it's almost like automatically the assumptions we made on this theory told us if you're going to make these assumptions, you're basically applying a traction load. It's interesting that it came out in that natural way. I didn't force it; it just came out to be that way. Um, and so, in reality, this is a situation where I'm actually really doing, um, and obviously I'm creating this at z equals L, right? That's where I'm doing it. That's really the moment. Think about it. Tx times this distance is a moment, and Ty times the distance is a moment. And the reason they're the negative to each other is because this moment causes a moment uh, clockwise, and this one causes a moment counterclockwise. So that's why it's opposite. But in reality, that's a moment. That's a moment. And so in reality, this right here is ML del alpha. So I'm able to relate the internal virtual work to external virtual work in a much easier manner because now I know this coefficient is moment. Um, and so I'm basically almost there now. So I'm not done yet. I need to now relate the internal virtual work to the external virtual work. And just for the kicks, I'll just write it here because I don't want to forget it. The internal virtual work was slightly more complicated. This is external virtual work. And the internal virtual work, I will try to go by memory. Um, I honestly don't remember it, and I don't want to go back. But I think it's worth trying it. So please correct me if I got it wrong. I think it was like that. And that was it. Well, we should check it because I don't want to make a mistake that will cost us time. The internal virtual work. Oh, it was in the previous slide. All I have to do is go to the previous slide. It's right here. And then I have the next term, which is plus. And we're really making progress here. Very excited about this because I'm going to show you that I'm going to tell you something very surprising when I'm done. And you're going to ask me why I wasted your time. But that's okay. Sometimes you have to go through stuff to realize you probably wasted your time. So why we don't integrate this by parts? I think it'll be fun to do that. We'll integrate this by parts. We'll do it my way, which is a highway. Sigma yz. I like doing it this way. It just tells me exactly what is going on physically. That's why I like it. I learned it from my professor that taught me this class. I thought it was great. Great idea. It just keeps everything so clean and so clear what is going on when you integrate with parts. You can memorize the formula, but I think this way really there's a physics to it. You know, there's a meaning. There's meaning to what you're doing, which is you're basically integrating parts. You're not using Gauss theorem. Yes, you are, but indirectly. We are applying Gauss theorem. We're doing it in a way that's unique and different from what you learned before. Now I'll put everything inside the integral, and I'll start collecting terms if you don't mind. And in the process of that, I'm going to go ahead and write out. I'm going to write out all the terms one by one. So internal virtual work equals external virtual work. So I have 0 to L, and I have integral of area, and I have x sigma yz minus y sigma xz, and then I have this is dA, that's dx, but I can combine this term with that term. So I'll say minus ml del alpha. And then I'll continue on. I have some terms I have to go into the integral, which are the ones here and here, and that goes back into the integral, but that's an integral over the volume, so it doesn't change the character of what the integral is, but it changes. Let me just continue here. Or if you want to see it, if you guys want to see it how it looks, so it's more clear. Sometimes it's better to write it that way too. I think it's kind of neat to see different ways so you can keep learning. And then we have the cross term become are evaluated on the contour, right? Because that's what integration part is all about. So I have plus over the contour. And then I have tau, not tau. I don't know. I'm used to using tau for shear, and so I apologize for that. But it's okay. We can use whatever convention we want as long as we're consistent. Check that out. Check that out. We found through principal virtual work, now I can apply the fundamental lemma of calculus to variations. And for any del alpha, for any del kappa, I can now come up with the Euler-Lagrange equations. And the Euler-Lagrange equations then have now come to something very simple. For any del alpha and for any del kappa, I have two equations that I should have gotten. And so the Euler-Lagrange equations then become partial sigma xz partial x plus partial sigma yz partial y equals 0. And then at the boundary, I found Cauchy's relationship. So this is the in the volume. And then on the surface, I have sigma yz and y plus sigma xz and x, and that's 0, and that's on the surface. That's on the surface. Well, on the lateral surface. Well, clearly, this doesn't look groundbreaking, does it? There's nothing groundbreaking here. One of the Euler-Lagrange equations is physical also. I mean, that's exactly what I showed you here when I did this equation. So I don't see anything here very exciting. Like what I got is what I expected. ML, I found to be the integral from 0 to L, integral of the area. And again, I didn't find anything really satisfying if you were to ask me. Yeah, I mean, this is clearly Tx and Ty when I use Cauchy's relationship. So I didn't really get anything fruitful out of here. I mean, isn't these the equations we could do in 3D? And this is the fact that I applied a moment. So it doesn't look like very useful right now. So alpha, let's remember here, alpha here is a rate of twist. And it varies, it's a constant. And when your z equals 0, there's no torsion, no rotation happening from point P to P prime. But as z equals L, you get the maximum rotation. So that's what that was. And so, you get this and you wonder, what am I supposed to do with this information? That's what it boils down to. And so for that reason, we have to cover the complementary virtual work to get anywhere with this. And so I'll show you that in the very next lecture. And so that'll conclude today's lecture. And we will then move on to complementary virtual work for the torsional problem, because there we will be able to then go ahead and actually solve the problem. Here, I don't think we made a lot of progress. These are the equations in 3D, and that's the very definition moment I came up with earlier. So it's not like it was revealing. It was not very revealing at all.